In the next, I will build a neural network-based data model to try to recognize those digit images as digits. The point here is not the neural network or the model or any of the technical details which would be learned in the semester, but the entire procedure of building data models, adjust parameters, do some evaluation, and adjust the design, this entire process of iteration, and eventually get some useful idea or a useful model. So let me directly introduce some of the components we will use. That is from the import. That is the neural network module. I use it as coordinate NN as well as generally speaking, the N module itself includes the useful components to build neural networks as classes. For those classes, you need to construct their instances to use in your model. And the functional module are some already instantiated classes. For those are useful when you do not need to adjust any parameters of the object and just use some already provided objects directly. We discuss this shortly. One of the most important component to build the neural network dealing with image data is called convolutional neural network layer. If we get an object, this is the name of class. By calling this class, we will get an instance of the class. The important attributes to assign for this for any particular instance of a convolution is how many channels of the input image. For this example, we have only one channel. That because that's grayscale image, and how many output channels? Just give it some number. For example, 64, and a kernel size. Kernel size means well, the size of the convolution kernel, which is a term, and we will study later. Consider that this particular conv1 object is processing operator, and this operator accepts a grayscale image and output a very special kind of image. This image has 64 channels and of similar size of the original image. We may have a look. Say jump conv1, and remember we already get a bunch of data. Yes, have a look at this temp. So look, 32 images, and each of that image has been transformed into 64 channels. And the size is similar to the original image, but with a slight difference. That is because at the border you cannot do the convolution operation. So yeah, so much for the details. Remove this, and we may want more than one channels. This second step of processing takes the output of the first step of processing as its input. So the number of channels would be, in this layer we get 64 channels. You have 64 channels here. Maybe we can expand the data a little bit more. Let us stop for a while and have a look what is inside one of the processing layers or the processing steps. To have a look at the internal of such an object as convolutional one, we construct a list of its parameters like this. We construct the list in this way. In a pair of square brackets, you write a for loop. It will construct a list, and with the element as the result of each iteration of this for loop. So if we have a look at this, we will see there are two elements inside, and the PS0 is a tensor. So that is 64 3 by 3 convolutional parameters. So in this operator, it has some adjustable parameters, and those parameters will determine the behavior of this operator. And similarly, there are corresponding parameters to determine the behavior of this similar operator. A convenient design is to have a container object, which we call it a neural network, and have all the layer objects in this container object as the overall data model. And then we deal with all the parameters in this overall data model in the training process. After adjusting all the parameters that fit the data and the task, we see that we have a viable data model for some task. The way to build such a container is to create a class inherited from the nn.module class, and call its parent class in the initialization of the container class. We then copy the convolutional layer object initialization stuff into the initialization of this class, and have the convolutional layer object as a member attribute. Do this for the second convolutional layer object as well. We would need more elements, but for the designing purpose, we leave it here and do the design the forward operation first before come back and add more elements. Design before we come back to add more elements. And the processing step happened in the forward path. It accepts an XX would be, in this case, I would write some comments here to suggest X batch of images. So how to process X? Let's say self.conf1 X, and okay, we then need some nonlinear activation stuff for processing the X to build some capacity to the neural network. For the details we'll discuss in class. So what we need is stuff like this here. Note this processing step and this processing step, these two steps does not have learnable parameters. They do have parameters, such stuff like that, but those are constant ones, or we can call it meta parameters. It's above the level, at the level of algorithm design, but not at the level of training the data model. So for whatever kind of data, those parameters remains constant. There is no adjustable parameters in these two objects, so we don't take these as the members of this class. Of course, you can create objects this way, but I just to organize stuff the way they are here to keep their rules clear from each other. Let's say dnet. We get a dnet object here. How it goes? Yeah, it works. Looks like that. So have a look at h equals dnet x. Oh, this x should be capital. Yeah, it works. Let's have a look at what we have got right now. Say I do not type print now here. That is 32 by 128, which is expected, and now each of the image has been shrunk to 5 by 5. This shrinking is mainly because of the pooling operations here, which would select the maximum element per 2 by 2 small area. In this way, each of the image would be represented by this number of attributes, 3000 something, and to have a processing layer to convert this number of representation of an image into a prediction of this class, we would need a layer called a linear layer. Takes such many inputs and 10 different outputs. The 10 outputs for each sample of the model have the interpretation of the model's judgment on how likely, how plausible to attribute this image into the corresponding digit class. H view. The view means we want to reorganize the numbers that represent an image into a long vector, which is 3200. Shape, that is the first element of the shape, which means the number of samples. That it should be 32 here always, and the second number I put 3200 here. Okay, and now after this viewing stuff, I put the change the viewed represented data into this linear layer. We would get an h of exactly 10 numbers per digit, per image. So let's try. Construct the net object and have a look at the h. Hooray! As expected. Look at what we got. Let's have a look for what it predicts for the first image. H0. Sure, not very meaningful. Because the first image is a 2, if you remember that. Show x0. It's better in this way. We can consider what we would like from the model. Now we have the model, but the model obviously has been just randomly initialized, and you cannot expect it behave in the way we desire. Now the next step of work is to express our desire of the way the model works, and formulate the desire in a mathematical way, and adjust model parameters so that the model follow our expectation. What we want to do now is to increase the number here, so much so that to express the model's assessment of that this image agrees very much with the 0, 1, 2, this class. Okay, we will see later.